The silence of the space vacuum is deceptive. We are used to seeing rocket launches as a triumph of fire and human genius. But beyond the boundaries of the Earth atmosphere, where the blue sky ends and the eternal night begins, the rules of the game change. Right now, the National Aeronautics and Space Administration is preparing a mission that is intended to return humanity to the Moon more than 50 years after the last human step on the regolith. The mission Artemis II is not just another flight. It is a test at the limit of the possible for 4 brave astronauts. Most media and viewers are focused on the majesty of the Space Launch System rocket, or on the moment when the Orion spacecraft will disappear behind the far side of the Moon. But professionals in the Mission Control Centers in Houston and experts from the European Space Agency hold their breath at a different moment. There is a stage of this mission that is almost never mentioned in the news, but which is critically dangerous. It is not the launch and not the landing. It is a complex, exhausting, and technically ruthless stage called High Earth Orbit Operations Demonstration. Imagine this. A ship with 4 people on board is squeezed between the hammer of Earth gravity and the anvil of the Van Allen radiation belts. For 24 hours, the crew will remain in a state of suspense, performing manual control of a multi-ton machine near the spent rocket stage. One wrong move, one mistake in the calculations of the approach speed, and the mission will turn into a catastrophe even before the Moon becomes visible in the portholes as a silvery sphere rather than a distant dot. Right from where you are watching, it is interesting to see how far our stories diverge. We begin. Why is this stage so risky? Why do engineers consider it the bottleneck of the entire program? In this video, we will move away from beautiful renders and dive into the dry but fascinating language of numbers, physics, and real reports from space agencies. We will break down every volt of energy, every kilogram of pressure, and every fraction of a millimeter that separates success from failure. You will learn how radiation exposure during this stage affects the cells of the human body, and why the heat shield, designed for return at the second cosmic speed, is only one part of the puzzle. Welcome to the world of real cosmonautics, where every step is a calculation, and every risk is the price of our future among the stars. To realize the true scale of the challenges facing the crew of the mission Artemis II, we must take a journey through time, back to the golden era of the space race. More than half a century ago, humanity already took a similar step. But a comparison of the Apollo program with the modern Artemis program reveals to us not only technological progress, but also a paradoxical increase in the complexity of tasks. In December 1968, 3 astronauts, Frank Borman, James Lovell, and William Anders, on board the Apollo 8 spacecraft left low Earth orbit for the first time in history and headed for another celestial body. It was a bold mission, the decision for which was made under conditions of severe time pressure and political pressure. Then, as now, the main issue was safety. However, the philosophy of risk in the middle of the 20th century differed significantly from the modern standards of the National Aeronautics and Space Administration. The Apollo 8 mission used a so-called free return trajectory. It was a brilliant solution in its simplicity of celestial mechanics. The ship was launched in such a way that even in the event of a total failure of the main engine while approaching the Moon, the gravity of our natural satellite would simply wrap around the ship and throw it back toward the Earth like a stone from a sling. This was a kind of cosmic insurance policy. In Artemis II, everything is different. The flight architecture is built on much more complex calculations, where the stage of high Earth orbit becomes a filter that tests the strength of not only the equipment, but also the human ability for ultra-precise piloting. Consider the technological abyss. The onboard computer of Apollo had an operating memory of only a few tens of kilobytes. Today, your ordinary electronic car key has more computing power. However, that simplicity also had its advantage. The systems were analog, straightforward, and predictable. The modern Orion ship is millions of lines of software code. It is an ultra-complex network of sensors and actuators where every second of the flight is controlled by digital algorithms. And it is here that the modern paradox lies. The more complex the system is, the more potential points of failure appear in it that cannot be predicted using ordinary logic. Special attention should be paid to the lessons that the National Aeronautics and Space Administration learned from past tragedies. Every detail of Artemis is literally written in the blood of the crews of Apollo 1, Challenger, and Columbia. After the fire on board Apollo 1 in 1967, where 3 astronauts died during ground tests, the approach to the choice of materials and the construction of hatches was completely revised. In the modern Orion, an atmosphere of a mixture of nitrogen and oxygen is used at a pressure corresponding to sea level, in contrast to the dangerous pure oxygen of low pressure in early Apollos. But why do we not use the proven scheme of a direct flight? The answer lies in scientific pragmatism. The Artemis program is not just a flag on the moon. It is the creation of a sustainable infrastructure. The Space Launch System rocket, which surpasses the legendary Saturn V in power, initially puts the ship into a very elongated elliptical orbit around our planet. This is done to test all life support systems in relatively safe proximity to the Earth, before giving the final impulse toward the moon. This stage lasts 24 hours, and it is an historical innovation that was not present in the missions of the 60s. In the 1960s, the Van Allen radiation belts were considered a serious obstacle, but the data from the first Explorer satellites were fragmentary. The Apollo astronauts flew through them at great speed, minimizing the time of exposure. In Artemis II, the trajectory is constructed so that the ship will remain in zones of increased radiation for much longer. This is a conscious step based on deep research by astrophysicists published in the journals Science and Nature, which analyzed data from the probes for studying the Van Allen belts launched in 2012. We now know much more about these radiation traps, but knowledge only adds anxiety for the electronics, which have become much more sensitive to ionizing particles than the old semiconductors of the last century. Historical context shows us an important thing. We are returning to the moon not because it has become easier, but because we have become wiser. However, every drop of wisdom in cosmonautics is accompanied by a new level of technical complexity. The transition from the analog era to the digital one, from a political race to scientific expansion, has changed the very essence of risk. Now, the danger is not that we will lack engine thrust, but in how we will cope with the management of the most complex machine that humanity has ever created in the most unstable environment of near-Earth space. To understand exactly how humanity plans to overcome hundreds of thousands of kilometers of hostile space, we must look under the skin of the most powerful technical system ever assembled in the workshops of the Kennedy Space Center. The Space Launch System rocket is not just a carrier. It is a colossal energy accumulator whose task is to overcome the shackles of Earth gravity. The heart of the first stage of this rocket is 4 RS-25 engines, which have a glorious history since the days of the Space Shuttle program. However, for the Artemis mission, they were significantly modernized. Now they are capable of operating at 109% of their nominal power. These engines burn a mixture of liquid hydrogen and liquid oxygen, creating a total thrust exceeding 8 million pounds. But the real complexity begins higher, where the interim cryogenic propulsion stage is located. This stage uses one RL-10 engine, and it is responsible for the most critical maneuvers in Earth orbit. The scientific complexity here lies in thermodynamics. Hydrogen must remain in a liquid state at a temperature of -253 degrees Celsius, while solar radiation in orbit can instantly heat the walls of the tanks. At the top of this fiery column is the Orion ship. It consists of 2 key parts that represent a triumph of international engineering thought. The first is the living compartment, or command module, developed by American engineers. It is a sealed capsule where 4 astronauts will spend about 10 days. The concept of a glass cockpit is implemented here with a large number of touchscreens and digital interfaces that allow monitoring thousands of parameters in real time. The second, no less important part is the European Service Module, created under the auspices of the European Space Agency. This is the utility room of the ship. It is here that the solar panels are located, unfolding in the shape of 4 wings, providing Orion with electricity. The service module carries supplies of water, oxygen, and nitrogen for the crew, as well as the main engine that will be used for trajectory correction and returning home. The life support system on board Orion is a separate masterpiece of biotechnology. Creating an artificial atmosphere in a closed space with a volume of about 9 cubic meters requires constant control of the partial pressure of gases. The main challenge is the removal of carbon dioxide exhaled by the astronauts. Reports from the National Aeronautics and Space Administration describe in detail the operation of the amine swing bed system, which uses special absorbents to clean the air. Unlike old systems, it is regenerative, which is critically important for long missions where every gram of mass is worth its weight in gold. Scientific journals, in particular Science, draw attention to the problem of thermal regulation inside the ship. In the conditions of deep space, one side of the ship can be under direct sunlight and heat up to 150 degrees Celsius, while the other side, which is in the shadow, cools to minus 100 degrees. To prevent freezing of internal systems or overheating of the crew, Orion is equipped with a complex network of radiators and heat exchangers that pump a special coolant through the outer shell of the module. Special attention deserves the emergency rescue system, the launch abort system. It is a small rocket mounted at the very top, which in the event of an anomaly at launch is capable of tearing the capsule with the crew away from the rocket in milliseconds and carrying it to a safe distance. This system must be active throughout the entire period of ascent into orbit, which creates an additional load on the flight control system. Thus, Orion and the Space Launch System are not just transport. It is a complex ecosystem where fluid physics, thermodynamics, and digital algorithms work in an inseparable connection. Every bolt, every line of code in the onboard system has undergone thousands of hours of testing, but space always finds a way to challenge human calculations. That is why the next stage, entry into high Earth orbit, will become the real moment of truth for these technologies. When the roar of the Space Launch System engines subsides and the first stage and boosters are left far below in the waters of the ocean, the most critical and least discussed stage of the mission Artemis II begins. Most people imagine a flight to the moon as a straight line, launch, flight, landing. But real celestial mechanics are much more insidious. Instead of immediately directing the ship to our satellite, engineers of the National Aeronautics and Space Administration planned a 24-hour pause in an extremely elongated Earth orbit. This orbit, known as high Earth orbit, has an apogee, the highest point, at a distance of about 74,000 kilometers from the surface of the Earth. For comparison, the International Space Station rotates at an altitude of only 400 kilometers. Why is this stage called the death zone? Firstly, it is here that the Orion crew becomes absolutely autonomous. Any critical error in the operation of the life support systems at such a distance no longer allows for an immediate return home. Secondly, it is here that a unique experiment will take place: the proximity operations and manual piloting demonstration. After separation from the interim cryogenic propulsion stage, which brought them into this orbit, the astronauts will not simply fly further. They will turn the ship around and begin to approach this huge empty rocket stage flying nearby. This is not just a test of piloting skills. It is a fundamental test of the optical sensors and navigation systems of Orion. Mission Commander Reed Wiseman and pilot Victor Glover will have to manually hold the multi-ton ship at a distance of only a few meters from the rocket stage, using only cameras and laser rangefinders. Imagine the complexity of this task. Both objects move at a speed of thousands of kilometers per hour in conditions of constant changes in illumination, from blinding sunlight to the absolute darkness of the Earth's shadow. Any wrong impulse of the orientation engines can lead to a collision. Since the rocket stage No is no longer equipped with its own stabilization system, it may begin to rotate unpredictably. Reports from the European Space Agency emphasize that this is the most complex approach maneuver ever performed by a piloted ship without the use of automatic docking systems. The physics of this process is described by complex equations of relative motion, known as the Clohessy-Wiltshire equations. In space, objects do not move the same way as on Earth. To catch up with an object flying ahead, You sometimes must first slow down to descend to a lower orbit and gain speed. This contradicts intuition, and that is why manual control requires hundreds of hours of training in simulators from the Artemis astronauts. In addition to the risk of collision, there is the problem of space debris. High Earth orbit crosses zones where spent stages of old rockets and inactive satellites accumulate. At such altitudes, the speed of a collision even with a small fragment of metal can be fatal for the sealed hull of Orion. Data from the United States Space Command constantly update the threat maps, but Artemis II will be the first mission in 50 years to spend so much time in this cluttered space before the final nod toward the moon. Why does the National Aeronautics and Space Administration take such a risk? The answer is scientifically justified. If the Orion systems cannot perfectly handle this approach stage within reach of Earth tracking systems, the ship simply will not be allowed to take the next step, the flight to the moon. This is the last exam, where the price of failure is not just the cancellation of the mission, but the loss of the ship and the crew in the deep vacuum. This stage is a real bottleneck through which the heroes of our modernity must pass before they see the far side of the moon. When the Orion ship completes its complex maneuvers in high Earth orbit, it finds itself in a zone that can be called the invisible minefield of space. We are talking about the Van Allen belts, two giant toroidal regions around the Earth where the magnetic field of our planet holds a huge number of energetic charged particles, mainly protons and electrons, arriving from the Sun or from deep space. The history of the discovery of these belts dates back to 1958, when the first American satellite Explorer 1, under the leadership of James Van Allen, discovered zones of such high radiation that the Geiger counters on board simply went off the scale. Today, thanks to data from the National Aeronautics and Space Administration probes for studying the Van Allen belts, we know that these structures are dynamic. They expand and contract depending on solar activity. For the Artemis II mission, these belts pose a double threat. Firstly, it is ionizing radiation, which is capable of penetrating the hull of the ship. High-energy protons colliding with the atoms of the aluminum hull of Orion can create secondary radiation, cascades of particles that are even more dangerous for biological tissues. According to research published in the journal Science, long-term stay in such conditions without proper protection can lead to damage to the DNA of astronauts, disruption of the central nervous system, and an increased risk of oncological diseases in the future. Secondly, it is a threat to electronics. Modern microchips of Orion are significantly smaller in size than those used in Apollo computers. This makes them extremely vulnerable to single-event upsets. When one charged particle flies through a transistor and changes the state of a memory bit from 0 to 1. This can lead to software errors in critical navigation or engine control systems. How do engineers solve this problem? Strategy of active and passive protection is implemented in Orion. Passive protection is the very structure of the ship and a special arrangement of cargo. In the event of a solar flare, the crew has a protocol for creating a storm shelter. Astronauts move bags of water and food to the walls of the living module, creating an additional barrier, since the hydrogen contained in water and polymers is the best protection against protons. A system called HERA, the Hybrid Electronic Radiation Assessor, is also installed on board. This is a network of sensors that monitors the level of radiation inside the capsule and on the skin of each crew member in real time using personal dosimeters. These data are instantly transmitted to Earth, where medical teams in Houston analyze the accumulated dose. It is important to understand, unlike Apollo 8, which flew through the Van Allen belts in a few hours on the way to the moon, Artemis II will be in the zone of increased radiation for much longer during the high Earth orbit stage. This is a conscious challenge. Scientific reports from the European Space Agency emphasize that successful overcoming of this barrier will be proof that our technologies are ready for long-term flights to Mars, where the radiation load will be even more aggressive. The Van Allen belts are not only an obstacle, they are a test of our ability to survive in the extreme conditions of deep space. Every centimeter of lead or polyethylene, every software check of code is a brick in the foundation of our future safety among the stars. But even after overcoming the radiation belts on the way back, an even more brutal test awaits the astronauts: the fiery entry into the atmosphere of the Earth. After the mission Artemis II performs its scientific program near the Moon, the crew faces the shortest in time but most physically aggressive stage: returning home. Space does not let go easily. The Orion ship will approach the Earth at the so-called second cosmic velocity. It is about 11 kilometers per second, or almost 40,000 kilometers per hour. At such a speed, the atmosphere of our planet ceases to be a soft blanket and turns into a hard, red-hot wall. The main hero of this stage is the heat shield of Orion, which is located at the base of the command module. It is the largest heat shield ever created for piloted flights. Its diameter is 5 meters. It is made of a material called Avcoat, a special epoxy resin with glass fibers. The principle of its operation is ablation. This means that under the action of terrible temperature, the upper layer of the shield melts and evaporates, taking away excess heat and not allowing it to penetrate inside to the astronauts. According to data obtained during the test mission Artemis I without a crew, the temperature on the surface of the shield will reach 2,800 degrees Celsius. This is twice less than on the surface of the Sun, but enough to melt any metal. The scientific journal Nature analyzed the results of the first flight and noted that although the shield worked perfectly, engineers of the National Aeronautics and Space Administration recorded uneven wear of the material, which forced them to conduct additional months of laboratory research before allowing people to fly. However, Artemis II will use a unique entry tactic that was not used in the days of the Apollos: the skip re-entry maneuver. Instead of diving into the atmosphere once and for all, Orion will first dive into the upper layers of the air, slow down, and then, using the lift of its hull, jump out into space again, like a flat stone jumping on the surface of the water. This is done for two reasons. Firstly, it allows for much more accurate selection of the landing site in the Pacific Ocean. Secondly, it divides the thermal load into two stages, giving the structure a chance to breathe a little before the final descent. During this maneuver, astronauts will feel overloads that exceed Earth gravity several times. Their weight will increase by 6 or 7 times. Around the capsule, a layer of plasma, red-hot ionized gas, will form, which completely blocks radio communication. For several minutes, the crew will be in complete isolation from the control center in Houston. At this moment, the only thing standing between the lives of 4 people and the fiery hell is a few centimeters of ablative coating and the flawless operation of automation. When the speed drops to sonic, at an altitude of about 8,000 meters, a cascade of parachute systems will begin. First, 2 drogue parachutes will deploy, and then 3 giant main canopies, each the size of a basketball court. These parachutes should slow down Orion to a speed of 30 kilometers per hour before a soft splashdown in the ocean. Successful completion of this block means that all the technologies we talked about earlier worked as a single mechanism. The heat shield is not just a piece of resin. It is the result of decades of research in the field of materials science and aerodynamics. It is the last barrier that humanity has learned to overcome to return from the heavens to the native land. When we consider the mission Artemis II, we should not perceive it as a linear path where everything is prescribed to the last second without the possibility of changes. In the world of high science and space engineering, there are always debates, alternative scenarios, and a huge number of blank spots that we are only beginning to fill. The scientific community, in particular the authors of articles in the journals Nature and Science, are conducting heated discussions about the feasibility of exactly this format of returning humans to the Moon. One of the main alternative theories concerns the question: do we really need the high Earth orbit stage with manual piloting? Some experts believe that modern systems of artificial intelligence and automation are capable of performing these maneuvers much more accurately than a person who is under the pressure of stress and physical overloads. However, the National Aeronautics and Space Administration insists on a human-centered approach. This is a scientific philosophy that states, in the event of an unpredictable anomaly that is not included in the algorithm, only human intuition and the ability for non-standard thinking can save the mission. This is what we call the Apollo 13 factor. What do we still not know? The biggest mystery remains the long-term impact of deep space radiation on the cognitive functions of the brain. Although we have data from the International Space Station, it is protected by the magnetosphere of the Earth. Artemis II will become the first laboratory in real time where we will see how the nervous system reacts to direct hits of heavy ions outside this protection. To monitor space weather and solar activity, which directly threatens the mission, the most powerful instruments of humanity are involved. The James Webb Space Telescope and the Edwin Hubble Space Telescope, although they look deep into the universe, provide critical data on the state of the interstellar medium and the activity of the Sun, which allows forecasting radiation storms. There is also a Plan B for this mission. If during the stay in high Earth orbit even the slightest malfunction is detected in the interim cryogenic propulsion stage, which is responsible for the push toward the Moon, the mission will not be canceled immediately. It will turn into a multi-day study of near-Earth space. This will allow obtaining unique data on the upper layers of the atmosphere and the Van Allen belts that cannot be obtained using automatic probes. This emphasizes the flexibility of the modern space program. Future missions, such as Artemis III and Artemis IV, completely depend on the success of this flight. Artemis II paves the way for the creation of the Lunar Gateway, the orbital station gateway, which will become a permanent outpost of humanity near the Moon. The European Space Agency and the Japan Aerospace Exploration Agency are already developing modules for this station, based on the telemetric data that Orion will collect. But the most ambitious goal lies even further. Every successful maneuver, every solved technical paradox of Artemis is preparation for a flight to Mars. Scientists consider the Moon as a training ground. If we do not learn to safely pass through the death zones around our own planet and our satellite, we will never be able to overcome millions of kilometers to the Red Planet. Artemis II is not just a flight to the Moon. It is a check of our readiness to become a multi-planetary species. We still do not know all the answers, but it is precisely the search for these answers in the darkness of the unknown that is the driving force of progress. We stand on the threshold of a new era, where the boundary between science fiction and reality is blurred under the roar of the RS-25 engines. The mission Artemis II is not just a technical report of the National Aeronautics and Space Administration or a political demonstration of power. It is a manifesto of human will that challenges the laws of entropy and the hostility of the boundless vacuum. Considering the most dangerous stage, maneuvers in high Earth orbit and passing through radiation belts, we see the true face of modern cosmonautics. It is not an easy walk, but a mathematically calculated and incredibly risky step into the unknown. Why do we continue to go forward, knowing about thousands of points of failure, about the threat of ionizing radiation, and the fiery hell at the entry into the atmosphere? The answer lies in the very nature of our species. As prominent philosophers and scientists once noted, man is a creature that strives to overcome his own boundaries. The Moon in this context is not the ultimate goal, but only a mirror in which we see our potential. Every second of the crew of Orion staying in the death zone around the Earth is a payment for knowledge that in the future will allow our descendants to call the solar system their home. Scientific data collected during this flight will become the foundation for the next decades. We will receive answers to questions about the biological endurance of humans, about the reliability of digital systems in deep space, and about the effectiveness of international cooperation where the United States of America, Europe, Japan, and Canada work as a single organism. This is real progress. The ability of a civilization to unite in the face of cosmic scales. When Orion finally touches the waves of the Pacific Ocean and the 4 astronauts breathe the salty Earth air again, the world will change. We will no longer be those who only dream of stars. We will become those who have learned to return from there alive, holding in our hands the keys to the future. This return is a triumph of the analytical mind over the chaos of the universe. We proved that even the most hidden and dangerous stages of the mission can be conquered if you have enough knowledge, courage, and technological excellence. we invite you to think, is this risk worth the knowledge that we receive? What meaning does the return of humans to the moon after 50 years of silence have for you personally? Share your thoughts in the comments. Are we witnesses to the birth of a multiplanetary civilization? Or is this just another flash of human curiosity in the ocean of eternity? Your participation in this discussion is part of a great story that we are writing together. Give a like and subscribe to the channel. The world of space is waiting for us, and Artemis II is only the beginning. We finished this story, but the study continues. See you in orbit.